Welcome everybody. It's wonderful to have you all here. My name is 𝗗𝘗𝗲𝗏. I'm a professor and Associate Dean of Research in Engineering at Monash University. I'm also the New Energy Theme Leader within the Woodside Monash Energy Partnership. Now, as a researcher, I'm focused on the development of new energy materials and technologies, which is very relevant to today's webinar. So it's a great pleasure to have you all here. This is the second of a four-part webinar series as part of the Woodside Monash Energy Partnership. And today we will focus on large-scale green hydrogen production. So it's a very topical and a very important issue facing Australia and the world. Now, before jumping in and hearing from our speakers, which are all here on video now, let me acknowledge that I'm hosting this webinar from the lands of the Kulin Nation. I acknowledge the traditional custodians of the various islands on which you all work today, and the Aboriginal and Torres Strait Islander people participating in this meeting webinar. I pay my respects to elders past, present and emerging, and celebrate the diversity of Aboriginal peoples and their ongoing cultures and connections to the lands and waters of Victoria, and more broadly across Australia where our listeners are joining. Now, let me also acknowledge the Monash Energy Institute, who are hosting the webinar today. The Monash Energy Institute brings over 170 researchers across three main impact areas: advancing new energy solutions, accelerating the energy transformation, and integrating a consumer-led future. Now, this series has been developed to showcase some of the major themes as part of the Woodside Monash Energy Partnership, which is a multi-year partnership between Woodside Energy and Monash University, with a key focus on advancing Australia's leadership in sustainable energy technologies and carbon solutions. So today it is about new energy technologies. That's the thematic, and we're going to talk about large-scale green hydrogen. We heard from our director, Professor 𝗗𝗲𝗏𝗍𝗍, in the first of the webinars where he provided an introduction to the partnership. The following two webinars will be featuring on carbon capture, conversion and utilization. That will happen on the 25th of November. And there'll be a final webinar on the 10th of December around energy leadership. Now, moving right along to today's theme, which is around large-scale green hydrogen. Many of you will know that the idea of a hydrogen economy has been promised for a long period of time. That clearly hasn't happened yet. But the world is transitioning to a low carbon solution, and energy solutions are being required, and hydrogen will play an ever increasing role in that future. Now, hydrogen is already actually used. It's actually produced at 70 megaton scales per annum. It's used primarily in refinery and ammonia production, with almost all of that hydrogen produced where it's actually used. So unlike LNG, which is transported all across the world, liquid hydrogen in general is a very confined use case. So there's a major challenge currently underway, which is around production of hydrogen and also transportation of that hydrogen. So for the world to transition to a net zero energy, or transition to this net zero energy carrier, there's a natural question. How do we in Australia capture that opportunity? How do we become a global export superpower of hydrogen? And ultimately, how do we do that in the context of green hydrogen production? So to help provide some context and insights, we have three wonderful speakers here today: 𝗗𝘗𝗲𝗏𝗏 from Monash, Stuart Walsh, also from Monash, and 𝗗𝘗𝗏𝗏𝗏 from Woodside Energy. Now, there is plenty of time to answer questions after the three speakers all present. And for that, I'd just like you all to use the Q&A box at the bottom of your screen to write any questions you have. And if you want to direct those questions to one of the speakers specifically, please use their name in there, and then I will read them out and direct them at the end. So without further ado, let me introduce our first speaker of the day, Dr. 𝗗𝘗𝗏𝗏𝗏𝗏. He's a research fellow within Monash University working on life cycle impacts of hydrogen production. He has extensive industry background as an engineer, a researcher in manufacturing, high-vac energy systems and electronics. He has published in several areas, including biophysical economics, renewable energy, life cycle analysis, energy storage, and energy economic modelling. So over to you, Graham. Thank you very much.
Thanks very much, Jack. I'll just share my screen. Okay, so I'm looking at life cycle impacts and I'm trying to understand those. I'm working in a team with 𝗗𝘗𝗲𝗿𝗀, Andrew Hoadley and Roger 𝗗𝗲𝗿𝗀. So we're looking at large scale hydrogen production. So really the most important thing and really the starting point is that the primary drivers for deploying hydrogen at large scale are environmental rather than economic. So there's a lot of ways we can make hydrogen, but if they're not environmentally sustainable, then there's really no point in doing it. But at the same time, it needs to be economic, otherwise nobody's going to buy it. Now, one of the key things to understand about renewable hydrogen is that the environmental impacts are embedded mostly in the plant rather than through operations. So from the day that the production starts, the environmental, or most of the environmental impacts have already started. So what we're looking at doing is how do we quantify those impacts? What are the uncertainties? And how can we use life cycle analysis and net energy analysis to support plant design and decision making? So one of the ways I'd like to frame this is that there's really two domains for looking at green hydrogen. There's the economic domain, which is nominal, so we look at prices and markets and so forth. Then there's the physical domain, which I think of as the real, what is happening in the real world. So in economics, there's money flows, there's prices and profit, and ultimately this is normally where decisions are made. But as I mentioned, if we can't produce hydrogen in a sustainable way, there's really no point in doing it. So we need to understand the energy flows, material flows, the real impacts and the net energy. So one of the things that we're trying to do is how do we link these domains and how do we resolve the tension that's often between them? So just focusing on the economic domain, one of the features of a market economy is that the full supply chain is distilled into a single cost. And this is, now if we look at the hydrogen production facility there, we've basically got the CapEx, which is a single cost or can be simplified as a single cost. Wind and solar are basically free, and we use that to produce green hydrogen. So it comes out as basically $1 per kilo, and it either works or it doesn't economically. Now it's treated as a commodity, but it will be subject to certification. One of the key ideas is that the input costs are mediated by markets that are only weakly or often inversely connected to environmental impacts, and we really need to understand those. And a key question is how green is the hydrogen? So if we move to the physical domain, we're less interested in the CapEx, but we're interested in what goes into the physical infrastructure. So we're looking at the plant and equipment. If we do a life cycle assessment, we start off with mining of materials and primary energy from nature. It goes through manufacturing, transport, and so forth. Now, to produce all that plant and equipment, there's of course waste and emissions to the environment. Now, one of the things about life cycle assessment is that there is no single numeraire that incorporates all flows. Flows are complex, multi-layered and recursive. So in other words, it's much more complicated than a simple market price. So what are the tools that we can use? We can use life cycle assessment, it's often called life cycle analysis, net energy analysis. And the project that we're looking at is including renewable simulation, optimization, and other statistical procedures such as 𝗦𝗽𝗲𝗿𝗀 simulation. Now, ultimately, all of this boils down to an impact or flow per kilogram of hydrogen. So in other words, we'd like to know the carbon emissions, the embodied energy, etc., per kilogram of hydrogen. So this is an example of net energy analysis where we look at the embodied energy of the plant and equipment and look at the cumulative energy returns over the lifetime of the project. So I've just given a simple example here where there's 20 petajoules of embodied energy invested in the plant and equipment, and it takes, if it's producing 5 petajoules of hydrogen per year, it takes roughly 4 years to pay back the original energy. Now, this is a key metric that can be used to assess just how sustainable an energy production system is. And this is one of the tools that we use. Now, there's many impacts that we're looking at. The headline impact is, of course, global warming potential, which all fossil fuels contribute to, but there's other things such as acidification, respiratory inorganics, and so forth. And then there's a host of other impacts. So some of the ones that we're particularly interested in with renewable hydrogen are the embodied energy, demand for critical minerals, land use, embodied carbon, and just the sheer scale. So this graph on the right is just here to demonstrate that a shift to low carbon electricity carries certain impacts that we need to be conscious of. So in this particular one, it's looking at selected metals under different scenarios. So as you can see, if we look at, say, copper, nickel, and aluminium, there's far more demand for those under low carbon scenarios. And this is something we need to understand and incorporate into our analysis. So a project that I'm working on is we're looking at a decision support tool to be able to put all of this information together. So some of the things that we're looking at is technology selection, scale, economics, and so forth. And we'd like to integrate all of these so that we can better understand the impact of large-scale hydrogen. So I'll pass it back to you, Jack.
Thank you very much, Graham. Clearly, the idea of, or the notion of comparing the economics versus energy is really important, because both are really important vectors for understanding. And that net energy analysis is not only critical, but ultimately very difficult, considering the supply chain and all the components that are needed. So it'll be really interesting to discuss what you've actually found in that regard for different types of hydrogen production facilities. So thank you very much, Graham. Our next speaker today is Dr. Stuart Walsh. Stuart is a senior lecturer in the Department of Civil Engineering here at Monash University. His work is focused on the development of tightly coupled geomechanical, hydrodynamic, and geochemical multi-scale models and their application in geoscientific and engineering problems. He's worked on a variety of practical problems around energy relating to the development of offshore oil and gas, geothermal energy production, carbon sequestration, and hydraulic fracturing operations. Today he'll talk about the mapping of resources, available resources for green hydrogen production. So over to you, Stuart. Thanks.
Cheers, thanks very much. I'll just share my screen and get it fired up. There we go. So thanks for that. Thanks for giving me the opportunity to talk about some of the work that we've been doing, looking at mapping some of the potential for developing different hydrogen operations. As Graham alluded to in his presentation, there's a number of different ways that you can think about putting together hydrogen production, a number of different ways that you can look at it. The good news is that at least over the last couple of years, we've actually seen some really exciting things coming out of the literature around what the levelized cost of hydrogen is going to be doing into the future. All of the different sorts of predictions that are out there are predicting pretty significant falls in what the levelized cost of hydrogen is going to be doing over the next 10 to 30 years or so, which is fantastic. But at the same time, we have a fair bit of complexity around this as well. In particular, if we're talking about green hydrogen, there's a number of different energy sources we can think about combining with a number of different hydrogen production methods, let alone the end users that we can target, or even the locations that we can be looking at as well. And in particular, that's the area that we're interested in. We've been looking at thinking about different ways that we can not only assess the different viabilities of these different projects, but also put them into context. So think about where they might be located in space. Because there's a need not just for analyses of the potential cost of these sorts of systems, but also an understanding about what they might mean for where they're located in terms of the people at those locations, in terms of the industry at those locations, and also in terms of potentially the policymakers as well, what sort of new infrastructure they might want to put in place. So what we're interested in doing is designing tools that can highlight economic potential for hydrogen projects. And in collaboration with Geoscience Australia, we've been working on ways of assessing this economic potential. So how do we go about doing that? Well, if we think about a typical hydrogen project, especially a green hydrogen project, there's a number of different things that we need to combine to make an assessment of what their impact may be. Number one is the mode of production, the mode of hydrogen production. Another one is the sort of the energy source that's attached to it, and also how big everything is. That's obviously very important. But at the same time, we need to place that project in space somewhere. It has to be located somewhere. And in particular, if we're talking about renewable energy systems, where you place that project is really important. Not all renewable resources are created equal in different places around the world. And the quality of that renewable resource is going to impact on the viability of your project, depending on where it's located. At the same time, though, especially in a country like Australia, where we're very, very large, we've got wonderful renewable resources in lots of different places, we need to be concerned, though, about what the available local infrastructure is. Your project is going to be affected by how close you are to ports, to roads, other transportation systems that you might want access to. So we're looking for ways that we can combine different assessments of these three factors, primarily, within one sort of code. And that's where the code that we've been working on in conjunction with Geoscience Australia comes into play. It's this code called 𝗗𝘗𝗲𝗏. Originally, the code that I've been developing was put in place to assess regional economic potential for mineral resources. And there, basically what we're doing is we're looking at different mineral deposits around Australia, working out in particular what it means in terms of their distance to infrastructure and the size of those deposits might mean for their economic viability. And if you're interested in those, I'll give myself a quick plug. We've got a couple of papers out around that. But working with Geoscience Australia, one of the things we realised was that this tool that we've developed for assessing mineral economic potential could also be applied in the hydrogen space. And in particular, we've put on an extension of that code looking at what we call the economic fairways of hydrogen production. The idea here is that we take an assessment of the viability of different forms of hydrogen production, both the energy source, but also the form of the production itself. We come up with assessments of what the cash flow would look like for that scale of plant under different assumptions about the capacity factor. And we build up a set of functions that we can use to determine the viability of those types of projects on different scales. But then what we do on top of that is we combine that with maps of the capacity factor around Australia and also the available infrastructure. And combining those things, we can come up with assessments of the economic potential and other impacts of these projects on a regional basis. So just to go into a couple of details about how these particular models work. Here is an example of the sorts of components of the calculation that we go through when we're thinking about assessing a particular site or a particular location. Basically, we combine different inputs about the size of the plant, the type of operation, that sort of thing. And then we can come up with economic assessments and also energy assessments about what the hydrogen plant will need. We can combine that with the power plant of a suitable size that's appropriate for the renewable resource at that location. Also combine the cost of the available infrastructure. And from there, we come up with assessments of cash flow and economic value are derived from that. Now, to be honest, this type of assessment is not all that different from what you would do typically if you're trying to work out what the cost of hydrogen is. What makes it a little bit different is that we're not just doing it at a single site, but we also do it on a regional basis. And in particular, one of the things we're really interested in is the interplay between the location of the resource, the scale of the hydrogen plant, and the available infrastructure that's at different locations. Because as I mentioned, Australia is a big place. Some places are better suited for hydrogen production than others, depending on how much infrastructure is available at those locations. So what does this look like when we put it in practice? Well, here's an example of just one of the sorts of calculations we might do. We're interested, for example, in assessing, how you might go about siting a hydrogen plant that uses some sort of solar energy as its energy supply. So we start off with our solar capacity factor, but then we combine it with our assessments of distance to infrastructure, transportation distances to the closest port, all those sorts of things, to come up with an estimate of what the potential value is of a hydrogen plant at a particular location. Once we do that, we can then rank it and then sort of come up with an assessment of which areas might be better suited than others for particular types and scales of hydrogen production in particular. You can sort of see that on the right-hand side. One thing that I want to point out about this particular map, though, is that you can sort of see two things going on here. One is you can clearly see for solar-powered resources, we tend to have better solar power in the northern parts and also in Western Australia. But in addition to that, you can also see that while there are particular areas towards the centre of Australia which have really good solar resources, they're not so well served in terms of the available infrastructure, distance to water and the like. And so that's one key thing that we want to get out of this particular code that we're putting together. It's the ability to be able to assess the different impacts of infrastructure on the viability of hydrogen projects. Because as we see it, it's not just a tool for the industry, it's also a tool potentially for policymakers to sort of say, well, if we put in an additional road or rail in this particular location, what would that mean in terms of the industry, in terms of serving the communities better and the hydrogen productivity better as well. We can also start to answer and ask and answer, I should say, different sorts of questions around how you run your hydrogen project as well, which is kind of interesting too. So one of the examples we've been looking at is thinking about the impact of alternative water sources. In Australia, especially when we're thinking about hydrogen projects, we are often concerned about water supply. It's a relatively dry country, and as such, we want to make sure that we're making the best use of the water that we have available. Hydrogen projects are liable to take a significant amount of water if they run, and so it's worthwhile considering whether or not we can work off alternative water sources. Two that have been identified are things like seawater or saline aquifers. We might also be thinking about running hydrogen off wastewater projects as well. What's interesting about this is when we can take our model and we can take, say, for example, locations of major populations as a proxy for wastewater treatment plants. Using that, we can actually make an assessment of what that type of water use would be in terms of the overall viability of different areas for hydrogen production. So the nice thing about that is actually if we compare our rankings from before and after, in our model at least, we're seeing that the use of these wastewater sources is actually not making that as much of an impact as you might think on the overall viability of different locations for hydrogen production. The reason for this sort of comes back to what I was saying earlier about the need for locating plants close to good infrastructure. It turns out in a lot of the places where we have good infrastructure, the reason that we have good infrastructure out there is because we also have people. People produce water, or at least wastewater. And so we can take advantage of that too. Anyway, hopefully this has sort of illustrated some of the reasons why we're interested in these sorts of codes and these sorts of programs, because lots of the questions around hydrogen development are big challenges. They're big scale projects. Different people will have different opinions about what they think will happen in terms of the relative cost of hydrogen production, the relative costs of different forms of renewable energy going into the future, even the price of hydrogen, even the end users of hydrogen as well. Having tools that we can all use, not just the industry, but also policymakers, even the public, to understand where these or how these different influences will impact the ultimate price of hydrogen will be really important to make sure that this industry takes off in the right way and gets used in the right way too. So thank you very much, and I'll pass it back to Jack now. Cheers.
Thanks so much, Stuart. That's fantastic. The idea of actually combining all those elements and starting to get maps of where the resource and scale of operation actually makes sense for a given hydrogen production plant, I think is fascinating. And the linking back through to even the type of water and the cost of that water and the nature of that water, I think that's absolutely critical as we move forward. So thanks very much for your inputs there, Stuart.
Yes, thank you.
Our final speaker for today is Dr. Ashley Roberts. She is an energy transformation engineer at Woodside Energy. In her current role, she is responsible for evaluating technological and commercial aspects of the hydrogen value chain, including the upstream energy resource production, midstream processing, storage and distribution, and end-use technologies. She's also had extensive experience as a business analyst, energy strategist, and commercialization officer for companies, governments, entities, and startups. So thank you, Ashley.
Thanks, Jack. Share my screen. Okay. So yeah, thanks for the introduction, and thanks to the previous speakers for such interesting topics. And I think I want to take just a little step back to talk a bit about what does an effective energy transition look like in general. So as outlined by the previous speakers, large-scale green hydrogen production is effectively a complex optimization problem. Interwoven with the technology are many layers of social, environmental, and regulatory factors that also need to be addressed. The World Economic Forum describes an effective energy transition as providing solutions to global energy-related challenges without compromising the balance of the energy triangle, which is shown here. The three aspects of the triangle are energy access and security, environmental sustainability, and economic development and growth. These represent challenges, but at their core, they're really the key opportunities for our future, and that's what I want to focus on today. This is clearly seen with the distributed solar, photovoltaics, and battery storage, which has enabled microgrids in areas of the world that hadn't had access to reliable power. Even today, over 800 million people around the world live without access to electricity. And this isn't really about the power or the green hydrogen, it's about the people and empowering them, giving them access to education, sanitation, and small businesses. I'm sure it's clear to us that are living in Australia that the opportunities related to large-scale green hydrogen look vastly different than they would in microgrid-empowered villages. But what I'm going to highlight is that in many ways, the challenges here can be more complicated. Australia operates within a very modernized energy landscape, which can add more layers of complexity to these enabling dimensions outlined by the World Economic Forum that are shown here. Some examples of how that can manifest within these 6 dimensions are within energy systems structure. That's largely dependent on the location and resources outlined by the previous speaker. And Australia is very isolated and characterized by vast distances, which really presents a challenge here. There's capital and investment. With the current global crisis, less capital may be available, and there's also competing opportunities to invest that somewhere else. The increase in investor activism, green funds, and the proposed pandemic recovery acts may push forward this investment in green regardless of the crisis. So there's really a lot of uncertainty, and this really highlights the need for the regulation and political commitment. So this is a critical component of success in terms of climate goals and investment, as well as developing hydrogen standards and safety regulations. Trade regulations and international relations play a huge role if Australia aims to be an energy exporter. So in the case of Woodside, not only do we need to make sure that we're abiding by any domestic regulations and standards, those also need to interface with whatever other countries we plan to export to make sure that we can accommodate their own standards and regulations as well. Then there's other topics of institutions and governance, infrastructure and innovative business environments, and human capital and consumer participation. And really here is another key area. We have to train for all these new industries. Many of these were not even options a few years ago, as well as raise consumer awareness and gain social acceptance. People are going to want to feel like large-scale hydrogen is safe, and that's going to offer them some sort of an advantage in their own personal life. So this is really bringing me to the main point, that the energy transition is not made up of these linear shifts in the fuel mix or some simple substitution of production technologies that can be achieved by any single policy or innovation or investment. But rather, the social, economic, and technological systems that are connected to the energy system need to co-evolve and shape the transition really in unity. And this is extremely complex. So I'll highlight some of the collaborative groups that Woodside's involved with They include the Australian Hydrogen Council as well as the International Council and a variety of other groups working on standards, government policies, international consortium, as well as research centers to try to develop the enabling technologies that we'll need to support a large-scale hydrogen development of the future. So now looking specifically at the large-scale green hydrogen production, there are a lot of challenges all the way through the value chain. So starting with the renewable energy source, some challenges are that it might not be optimally located and it will always be intermittent, and that's can be overcome through stabilization from stored electricity or adapting the downstream processing to cope with this variable flow of hydrogen. This isn't typical in most processing situations, so this does require a different operational format. Using currently available commercial technology, the only viable approach to water splitting today is electrolysis. The main challenge there is that this process requires a large amount of energy to release the hydrogen. Most of today's electrolysis technology will require at least 50 kilowatt hours per kilogram of hydrogen. So the electricity must be extremely low cost in order to reach the $2 to $3 targets that are set by national strategies today. New technologies are under development, though, to improve the water splitting performance and also lower these costs. As for distribution and storage, hydrogen is a very low density gas, so it's very inefficient to transport unless it can first be compressed, liquefied, or attached to some sort of carrier molecule. These include liquid organic hydrogen carriers, ammonia, or even green methane. Each of these approaches has both pros and cons from technical, safety, and environmental perspectives. And it also really depends on the downstream needs of the customer because these aren't really interchangeable molecules. Hydrogen for transport requires commitment to adopt fuel cell electric vehicles. Large-scale hydrogen production is best suited for refueling stations with concentrated demand, such as bus depots, tethered trucking fleets, warehouses, ports, and airports. Many of these customers will require reliability and will want local service to be offered with the vehicle. This requires a large amount of collaboration all across the fuel cell electric vehicle value chain. There's already a large global hydrogen market that supplies industrial customers for fuels, chemicals, and materials, as Jack mentioned in the introduction. However, in this case, hydrogen is an industrial feedstock, and the price of green hydrogen will be much higher than what's currently used for the on-site brown hydrogen generation. In spite of this, there are a lot of producers that want to become green, and they may be able to absorb the cost of green. And this is especially true if they have advanced products like, let's say, a car, then the cost of green steel is a very small component in the overall price of the car. Power generation and using hydrogen as an energy storage vector to stabilize the grid has a lot of opportunity. We see this already occurring in other parts of the world, especially where the hydrogen generation can be co-located to absorb any curtailed power from a renewable energy source. And then it can release this when there's demand. The trade-off here is really the efficiency and scale when you compare hydrogen to other technologies like batteries or pumped hydro. Finally, we come to export, which is the extreme distribution challenge because the transport distance is very far. Not only that, but we need to comply with international maritime regulations, as well as work with shipbuilders to adapt their vessels to accommodate these new types of fuels. So that brings us to the more technical challenges, but I hope that helped to highlight that it's not really a technical problem. It's a very complicated cultural, societal, and world problem. It's a challenge that we face. So in addition to the projects on life cycle analysis and the systems analysis of renewable power generation, those are projects that Woodside actively investigates with Monash and otherwise. Another interesting topic that relates specifically to hydrogen export is to develop innovative tank designs and improve materials for large-scale liquid hydrogen storage. Containment of liquid hydrogen requires materials that can withstand extreme cryogenic temperatures of just 20 Kelvin. The only liquid colder than hydrogen is helium. Our work with Monash researchers must first develop models to better understand heat flows within a specific tank design. No matter how good the design is, there's always some kind of heat entering the vessel, and that's especially true during loading and unloading. This is going to produce boil-off gas. So another part of our modeling work integrates efficient methods to manage boil-off gas, which then will reduce or even eliminate hydrogen losses through the value chain. We also aim to develop better performance and low-cost insulation materials. These materials will improve the large-scale tank performance, and they can also be applied to other areas throughout the value chain, such as loading lines and cold boxes. An example of modern insulation materials includes microbubbles and aerogels, which can be incorporated into vacuum and multi-layer insulation systems. I also think it's really important to highlight the challenge of building capability across the enabling dimensions discussed earlier. Large-scale green hydrogen production is a critical path in our energy transition, and to create it, we must enable innovation through a diverse and inclusive workforce, devote time and resources to gain expertise, and invest in research and emerging technologies. Most of all, we need to support each other and work together. So, thanks.
Your messages around actually the complexity of the energy transition are really, they hit home, and particularly around the need that actually the energy transition is underpinned with sort of many competing investments and options. And so there is that need for new dimensions to be opened up and enhanced collaboration. And in particular, there's also technological challenges that need to be addressed around ultra low cost electricity, electrolyzers, transport, and I guess then there's the uptake, the use cases. So there's plenty of challenges across there. So that collaborative piece is really important. So thank you very much, Ashley. That's fantastic. So that winds up the presentation parts. I'd like to introduce or welcome back all the panelists here to the forum, and I will direct some of the questions that have been asked. Some of them have actually been answered in part, but I will address them anyway because they're not shared more broadly. So the first one I'll actually direct to Stuart. Stuart, there was a question there. Great presentation. This is from Benjamin Gavin. Great presentation. It seems from your graph of Australia that there is not much resource potential for South and Central Australia. There are many projects in hydrogen, blue and green, going on already with arguably adequate infrastructure in these locations. Can you comment?
Oh yeah, I mean, the whole thing about hydrogen is it's multifaceted. So the graphs that I'm showing there basically highlighting the fact that the best spots for good solar production. But there's many different ways that you can think about hydrogen and hydrogen production, which makes it really kind of flexible and versatile. I think that's why it's got a lot of potential, but also what makes it really tricky to model. But you can think about hydrogen production with wind, for example. You can think about it as a combination of wind and solar. You can think about it as having load balancing capabilities. You can think about using it with curtailed energy. There's just lots of different options, depending on what your assumptions are about the size of the plant, about the market. There's different maps that are going to come out of our model. I'm just showing off one potential scenario. But yeah, definitely in the South, part of the reason there is because there's different opportunities available. And that's why some of those projects are going ahead, usually with some wind or maybe even some hydro or something like that involved as well.
Okay. Yeah, just to clarify, your models don't actually account for the transportation part. It's really just up to the production point.
No, we do transportation as well, but we are primarily off-grid. That's one of the other things as well as about us too. So we're currently, hopefully working with Woodside to put together some grid-connected hydrogen models as well. But at the moment, most of our sort of models deal with off-grid hydrogen production. But transportation is included in there up to the port, and then beyond that, it's up to them.
Okay. Ashley, maybe a tough question, but an important one. There are many forms of hydrogen. You mentioned brown. There's also blue and green. There's a comment from Lincoln Turner. Chief scientist recently commented on ABC Radio that the window for blue hydrogen has likely already closed. What are your thoughts on that? Is that appropriate? Is it not?
Well, first I'll preface that, hopefully highlighting the complexity, also that I am just one individual, and, Woodside is a large company and makes a lot of its own views. But I guess to answer that in a way that makes sense to me is that I don't know how much the rest of the audience keeps up with current events with hydrogen, or, like the most recent news posts or even technological breakthroughs. And I guess at the core of this is highlighting how technology can advance at such a rapid pace. It outpaces a lot of other elements of society, such as policy, standards, social acceptance, even within business processes of being able to make decisions really rapidly, because the market is so dynamic, and so is the technology that's being developed. So even if you looked at this whole thing about hydrogen 2 or 3 years ago, no one would have thought even where we are today was possible at all. And it's accelerating so quickly that I think I would be doing a disservice to say anybody really knows. It really depends a lot on those policies, a lot on the relationships that are made and who's working together, and what technology becomes available in time in order to enable the transition. And it's likely that all of those colors or different emission factors have roles to play depending on the system. And as we saw, there's a lot of really complicated dynamic systems. And in a particular one, one sort of avenue is going to work better than another one. But green is accelerating very rapidly, and everybody, admits to that and wants that to happen.
Thank you. There's a few questions going on here that relate to water, and in particular desalination. I don't know whether this one would be more around Graham and Stuart, because that desalination is so energy intensive. But maybe Graham, I don't know if you're comfortable to talk to that, but what are your views around desalination as a source of the water, and then what are the energy impacts in terms of the post-production sort of costs for that hydrogen?
Yeah, well, of course, it is an issue. There's I think it's roughly about 10 litres of water per kilo of hydrogen. So hydrogen production is quite water intensive. The work that we've done shows that it's actually a fairly minor component in terms of both embodied energy and cost. So any plant that's located near the coast, desal is probably the way to go. There's, of course, issues such as brine, that need to be dealt with. Overall, it's a fairly low proportion. So, when you look at scale, when you look at sort of megaton scale of hydrogen, I mean, it's a lot of water, and you wouldn't want to be producing it in the middle of Australia, say, where there's no water. But providing there is if it's anywhere on the coast or there's a large water supply, it shouldn't be an issue.
Yeah, and that matches up exactly with our modelling as well. We're seeing exactly the same thing. It's in and of itself, desalination is an expensive thing because you're just selling water. But if you're selling hydrogen, then it's a small fraction of the overall cost. And so, yeah, and the difference in terms of the amount of water that you need between saline source and potable source is not that great in the overall scheme of things.
Yeah, I'd concur and just add that Woodside did a study with Monash on this last year because it was a critical topic, and found that overall, especially compared to the energy consumption of electrolysis, let's say, it's quite small. But we are also investigating direct seawater electrolysis, and there are potential options for that, but that's of course a much longer term development, which would take 5-10 years or more to make that a reality. So desalination is viable in the short term for sure.
Picking up on the point of cost, I guess these are all sort of interrelated questions. There was a question here from Suran Thurarayan. Is the $2 a kilo for hydrogen cost target appropriate, and can we achieve it in the foreseeable future?
Well, I don't want to bank my reputation on it. So $2 US, sure. I think that would be the way to go. So I think lots of people have different opinions about what the $2 means, but I think if you're aiming for $2 US, I think that's something that we could potentially, it looks like there's lots of predictions anyway out there that will be saying that we'll be targeting that. So often these sorts of targets become a reality because they're the things people are aiming for. So $2, why not?
Graham, in your modelling around energy on that point, how low would electricity need to be to approach that value for electrolysis produced hydrogen?
Most of my work has focused on the life cycle assessments side rather than the pure economics. I mean, $2 is potentially available, but I think that's also classified as a stretch goal, and it really depends on what the hydrogen will actually be used for. So the way I look at it is that if it's treated more as a premium fuel, a premium green fuel, it probably won't need to get that low. Where people are looking at it at that price is more of a universal fuel that's used to say as a replacement for natural gas. But if it's treated more as a premium fuel, it will find a lot of applications and it probably won't need to be that inexpensive.
Okay. So just
you can do a simple calculation just based on the energy consumption. So if you're talking about electrolysis today, that's why I highlighted there's about the 50 kilowatt hours per kilogram. So you can easily back calculate, and that's why you'll hear a lot if you do read like the national reports of wanting targets of 2 to 3 cents per kilowatt hour for electricity. But then you have to realize that electricity cost doesn't just mean the production cost. You have your transmission costs, and also may need to purchase LGCs in Australia. So even if your power is produced from a green source, you still have an LGC credit that you could either sell or keep for yourself. So that's an effectively a cost also. So definitely is expensive when we're using electrolysis. Anything that we can do to improve the efficiency and lower the electricity costs has a huge impact on reaching that $2 target.
Thank you. I mean, it's well on its way. There are examples of prices now around the world at that 2 to 3 cents a kilowatt hour. So I think the future is green. There's a question here from Roger Dargaville for you, Graham. Where do you see the greatest embodied energy for green hydrogen production?
You're looking at solar, PV and wind. Definitely with solar, it's the modules. It turns out that the electrolysis plant is a fairly small proportion overall. So the embodied energy of the panels really needs to come down, and it has been coming down. Wind works out better than solar. It hasn't come down as rapidly, but it's already better. It's a more straightforward technology, wind, in terms of the conversion of the working wind to basically power, whereas solar requires highly purified silicon, and that's a very energy intensive process.
Okay, thank you. This one's from Mark Heineman. Ashley, I'll sort of reframe it a little bit, but what do you envisage would happen to the LNG market as others stating net zero by 2050? And if so, what do you see as Australia's ammonia ramp up to ensure we maintain? Look, maybe I'll skip that one. It probably didn't read that right. This one's probably easier to address and to say. So Ashley, this one's from Jack Murphy Cruz. Thanks for the presentation. On that $2 a kilo stretch target, how important are government net zero announcements for countries that are potential hydrogen export markets such as Japan? Have you seen much interest from such off-takers to pay a green premium?
That's an interesting question. And I look back at the other one, I think I might understand what that one's saying too. And in both of those questions, I think highlighted the main part of the answer is that if Woodside is a energy provider, we really have to work with downstream customers and what their demand is. So definitely if customers are demanding or requiring green, then that's something that we would want to deliver for them. At the same time, if they want their energy delivered in a particular form, whether that needs to be pure hydrogen or they want it as ammonia, then we need to try to work with them to do that, because each has an advantage, and even LNG, if we're replacing coal or some other type of more pollutant source, then there's going to be an advantage to doing that. And I think we spend a lot of time. I don't even know how many employees at Woodside, I'd say at least, well over 50 that work on these kinds of questions, both with climate and customer offtake and regulations and standardization. So all of that is really critical. That's not a decision that we can make. And that's sort of what I wanted to highlight, is it's not just up to a company or a person to make all these decisions. We're working within a really complex and dynamic environment, which we want to respond to and deliver for value for the company, and also working towards climate goals, definitely.
Okay, thanks for that, and for helping to interpret that question. This one's from Chloe Munro. Wastewater seems like a great alternative, as it has, this is to brine and other forms of water, as it has to be treated anyway, so the marginal cost is very low. The question is, would there be enough wastewater? And does it make sense to locate hydrogen production near population centres and build more transmission to bring, sorry, my thing just jumped here. The question has just been moved. Maybe let's start off with that question around whether it's important to, or there's an opportunity to bring production near population centres where there is large wastewater reserves.
Yeah, well, I'll just answer that one in part. I'm sure other people have other opinions as well. I mean, this is some of the tricky things about hydrogen. If it takes off as a fuel, then you probably want it close to population centres, because you want to be able to get the fuel to the vehicles. Likewise, there's plenty of industry that will want the hydrogen too, because industrial heat is another one of those, I guess, a bit of a stretch goal, but still a goal. And then there's sort of transportation options, trucking and those sorts of things. So having them near population centres might actually, well, it's probably better than having it way out in the middle of nowhere where we can't get at it. So yeah, I think it's great. It's whether or not they've got the scale. Well, that sort of depends on what the demand is, and well, we have to see what that demand is going to look like as we go forward. So that'll be interesting too.
Okay, thank you. Look, given the time, I think we'll start to wrap up. There are a few questions here. We'll aim to get those questions answered offline and provide feedback on the website where possible. Before finishing up, I would like to ask each of the panelists here to just briefly mention what is the big thing that you think needs to be addressed as a priority to supporting large-scale green hydrogen production and ultimately export. So I'll start off, maybe we'll reverse the order this time, and we'll start off with Ashley, then go to Stuart and finish up with Graham.
Thanks, Jack. Well, I think most of those things have been addressed, but definitely working within the policy framework, things that have to do with, emission reduction targets, as well as price on carbon, and trying to just meet those downstream demands of the customers. When we're talking about domestic versus export, there are some very different challenges, and that I think was highlighted in these systems, where domestically you can be near your customer. That of course reduces all kinds of issues with the transportation and distribution. But if we're doing export, then there are some significant technological challenges that also need to be addressed to make sure we can send hydrogen at those large scale and across long distances.
Thank you, Ashley. Stuart?
Yeah, from my perspective, I think there's this really interesting question. I don't think I'm actually qualified to answer this one, but I think there's smart economists out there who might be, which is what do the contracts around these things look like? Do we, there's probably not going to be a spot market that opens up straight away. So how do we put a longer term contract in place? What does it mean in terms of the market dynamics, and how is the risk shared between the end users and the producers of hydrogen? What's the right balance for that? I don't have an answer for it, but it'll be interesting to find out if we find out one, that's for sure.
Fascinating. Graham?
You know, one of the things that we keep coming up against when we think about optimising renewable electrolysis is intermittency and turn down. Traditionally, large-scale chemical plants run at full capacity and they're not designed for turn down. And trying to get our heads around that and trying to get our heads around seasonality. I've kind of joked that we almost need to bring in some farmers who are used to dealing with seasonality and variability. And it's kind of like a different mindset because these are difficult technical challenges, and trying to work those out is going to be a definite challenge.
Well, thank you very much, Graham, Stuart, and Ashley, for your insights today.
Jack, if I may make one final comment.
Sure.
Just that I noticed some of the questions and comments today and before, and having been someone in the academic field and now working at Woodside, I just would really like to encourage anyone who is interested in these topics and in, you know, the greening of our energy mix to think about coming to work at energy companies. And there's a lot of new opportunities coming about all the time, and I think people would like you to be involved and definitely, you know, to get in and make a difference in this field, and yeah, see what there is to find.
That is a fantastic way to finish up, Ashley. Be part of the solution and not part of the problem. So I think that's excellent. Thank you to you all, Ashley, Stuart, Graham, for your time today. It's been a really interesting discussion, and there's been a fair different sort of perspectives provided on what it's going to take to produce, transport, develop hydrogen, green hydrogen production here. And obviously it's something that's of an immensely large challenge that we have to work together to try and address. So thank you again, and thank you to all of the listeners and the audience members here, both for listening and also for asking the tough questions, which we always welcome. And we hopefully have managed to answer some of those questions, and we'll hopefully get back to you on the others. This concludes the formal part of today. I would just like to finish up by saying that, again, this is the second of a 4-part webinar series. The next one's going to be on the 25th of November. It will talk about carbon capture, conversion, and utilization. And the 4th webinar will be on the 10th of December, where we will be discussing energy leadership. Now, there's a link here in the chat function that Nancy put through that will connect you through to those events, and you can have a look and register in your own time. So on that note, thank you all. Have a good evening and enjoy.